Today we're going to take a look at 7.7, transforming exponential and logarithmic functions. The nice thing about this section is that it's really the exact same thing as what we did last chapter when we worked with polynomials. We're going to use the exact same formula to do transformations of logarithmic and exponential functions as what we did with polynomials, this formula down here. The one thing that we need to just remember about it though is what do these variables represent. So the a value shows us two different things. The first one is that it's going to be a vertical stretch or compression, and the second one is that we would have a reflection over the x-axis. The b value is going to be the same exact thing as what the a value was, but this b value is going to be affecting the x, whereas the a value was affecting the y. The b value then is going to be, instead of a horizontal stretch or compression, or instead of a vertical, it's going to be a horizontal stretch or compression, and instead of being a reflection over the x, is going to be a reflection over the y-axis. H and k then are going to be similar to each other, one affecting the x, one affecting the y. These are your translations. So h, since it's affecting the x, is going to be left or right, and k, affecting the y, is going to be up or down. If you're asking yourself, why do we skip the f is just the thing that's going to represent your function, as in it's going to be the parent function that you're dealing with, the one that's going to show where your transformations are. So the two f of x's that we're going to be dealing with, the three different functions that we're going to be dealing with, will be an exponential function, which will just look in the form of b raised to the x power. If you take a look, there's no a times b to the x power. That a is actually going to be representing a transformation. So our most basic parent exponential function is just going to be a number raised to the power of x. It could also be, in terms of the log functions that we dealt with, it could equal the log of x, or it could equal the natural log of x. Those are the three functions that we're going to be talking about doing transformations with, and then again, it's just a matter of what's a, b, h, and k. So let's take a look at a problem we're talking about our transformations. So we're going to graph the parent function. We're going to go through and name a couple things to help us actually graph this parent function, like the y, in this case the y-intercept, because it's an exponential function, it has a y-intercept. Another point to help us actually do the graph, because remember, when we graph, we actually have to name points. We can't just go through and take a sketch from our calculator and say it's a graph. And then the asymptote. That's going to help us show where this graph is getting closer and closer towards as it goes one direction or the other. Then we'll name the transformation, apply that transformation to those points to be able to get the new graph. So first thing we want to be able to name is, what is the parent function? This is the function with the transformation. Our parent function then is just going to be the basic equation that we have. This is an exponential, so the basic equation of the exponential is just going to be the number raised to the power. So our parent function, if we want to call it f of x, is going to be equal to 3 raised to the x power. So we're going to bypass that 2. That's going to be one of the transformations. The y-intercept to our parent function, if we don't know what that y-intercept is, we know it's an exponential, so it's got to look something like this as we go through, although that again is just a sketch. If we want to try to find that y-intercept, we can just fill in a value of 0 for x and see what happens. So we plug in 0 here, say what is 3 to the 0 power? That's 1, so our y-intercept is going to be the point 0, 1. We need to name another point. Well, technically we found this point by just plugging in 0 for x, so let's just plug in another number for x. Easy number to use would be 1, and see what happens when we plug in that point 1. Well, 3 to the first power is just going to be 3, so we have the point 1, 3. And since we know it's an exponential function, and we had that sketch here of it going like this, that means that our asymptote is going to be the x-axis. Horizontal line means our asymptote is going to be y equals 0. And we go through and plot these points. So 0, 1 is right there, 1, 3 is here, and we have the x-axis as being our asymptote. So we can go through and say our graph is going to be really, really close to the x-axis, and then it's going to go through those points there. There's our parent function. Now, if we want to find our transformation, we take a look at what's added to this function here, what numbers are thrown in with this one here, which is that 2 there. Look at the location of the 2, how that 2 is being associated with the 3x, multiplication with it. That means that that 2 value is really going to be the a value, which in this case, our a value represents a vertical stretch by 2. And that's what we're going to use to apply to these points. Well, think about this. If you vertically stretch something by 2, which variable is going to get affected? That's going to be the y. It's outside, so we know outside not in associated with the x, so we know that it's got to affect the y. And how do we actually stretch the y's by 2 is we need to multiply them by 2. So we're just going to take each one of these points and we're going to go through and we're going to multiply our y's by 2. So the point 0, 1 becomes the point 0, 2, the point 1, 3 becomes the point 1, 6, and a horizontal line that's at 0. Think about the point, or take a point that it actually goes through, like 0, 0. If you multiply that y by 2, does that point really change any? It stays at 0, 0. So our horizontal line isn't going to move anywhere. It's going to remain at y equals 0. So let's just go through and put this information on our graph. There's 0, 2. There's 1, 6. Still have a horizontal line at y equals 0. And now we just have to draw a graph that goes through that. So it's going to get closer and closer to the y-axis, but it's going to be a little bit higher because we're multiplying everything by 2. And then we're multiplying the y's by 2. There's our graph of 2 times 3 to the x power. All right, let's take a look at 2 more examples of being able to go through and do the graphing. This one is 2 to the x minus 4. We're going to do the same exact thing, but we have less information here. It just asks us to be able to graph the function, so we don't necessarily need to graph the parent function. We need to describe how it's changing from the parent and then go through and do that same thing. Let's have some points, transform those points, transform our asymptote, and be able to get that information. So our parent function would just be 2 to the x power. We don't have that minus 4. That's our transformation, which if we take a look at that transformation, that's not affecting the x. Otherwise, we would see it in there with the x up in the exponent. So that means it's got to be the k value is negative 4, which that transformation is just going to be down 4. Which variable gets affected when you move it down? That's going to be y. And what are we doing to the y? We are subtracting 4. So we know that when we find all of our information, we're just going to have to subtract 4 to be able to find those new points. So it's another exponential function. So it's going to start off looking like this, meaning we're going to have a y-intercept now. Well, just as we found the other y-intercept, we can plug in 0. Well, 2 to the 0 power is going to give us 1. So we have a y-intercept of 1. We can find another point now. Well, the point that we have, we can plug in another value. So how about 1 into this? 2 to the first power, just going to be 2. And then we can name our asymptote, which our asymptote, again, is going to be that horizontal line, y equals 0. It's going to be the x-axis. Now we just need to apply these transformations. We need to take each one of these points, move it down 4. So this is going to become the point 0, negative 3. This will become the point 1, negative 2. And our asymptote, now, horizontal line, can we move it down 4? Think about this. We start at the point 0, 0, could get moved down to the point 0, negative 4. So a horizontal line going through negative 4 on the y-axis is going to become the equation y equals negative 4. Let's just plot this information. So 0, negative 3. There's our new y-intercept. 1, negative 2. Is that point there? We're going to have this curve going through here, this exponential graph going through there. Let's put in the asymptote. The way that we draw in an asymptote to be able to show, hey, this is where it's getting closer and closer to, that we can actually draw on this line now, is we can make a dotted line, horizontal line here. We can just make a dotted line going through that basically says, this isn't my asymptote, this is where the graph is going to get closer and closer to, and then we can actually just now draw that graph in there. And that's what our exponential looks like, 2 to the x minus 4. All right, the second one, negative natural log of x minus 4. Well, if we cut out that extra information, we cut out the negative, we cut out that minus 4, what we're really left with is just the natural log of x. So there's our exponent, or there's our parent function. It's the natural log of x. Remember, it's not an exponential, so it's not going to look like this. It's a logarithmic function, so it's going to look like this. This is what our basic log function is going to look like. Our transformations that we have, a negative out in front, so our a value is negative 1, which is going to imply that we have a reflection over the x, which what is actually going on when we have a reflection over the x? That is meaning that our y values are getting negative. And if we don't remember that, take a point like this one here, the point negative 4 or 5, we reflect it over the x, it becomes negative 4, negative 5. And so the value that's changing there, y went from positive 5 to negative 5. We're making the y's negative. And then we have this negative 4 inside with the x, Well, since it's inside with the x, that's telling us that that's the h value, which, remember, inside is opposite, so h is actually a positive 4, which is going to be a right 4, which, what are we doing when we move right 4? We are taking our x's and we are adding 4 to those x values. So our changes. Now, if we take a look at this graph, we have now a vertical line as our asymptote. We don't have then, because that's our asymptote, we don't have a y-intercept, but we do have an x-intercept. So we can go through and say, what is our x-intercept? Well, if we're not quite sure what that x-intercept is, to actually say what it is, remember, which value is going to be 0 in an x-intercept? Y is going to be 0. So if we actually plug in 0 here into our parent function and say 0 equals the natural log of x, change this out to solve for the x, that's base e. Use the circle method to rewrite it. E to the 0 power equals x. Anything to the 0 power is 1. So we have an x-intercept of 1. We can name another point here. Well, let's think about an easy value that we can plug into this. Remember, this is base e. An easy number to plug in here would be e. To be able to say log base e of e, that we have that going on, that when we see those two things there, that's just equal to 1. So we would have a value of e1. This, when we transform it, add 4 is going to become the point 50, but we need to also throw in our reflection over the x, which means make our y negative, so the 0 still going to stay as 0. We move the e to the right 4. Remember, e is approximately 2.7, so when we add 4, we're going to get approximately 6.7, and then we have to reflect that 1 across the x-axis, making the y negative, means it's going to become a negative 1. And then the last thing we can name, so there's one point, there's another point, is the asymptote. Well, it's a vertical line now, so it's going to be x equals 0. We need to move it right forward, which will actually take this and move it right forward. But when we reflect it, you can't really reflect a vertical line across the x-axis. It's not going to change anything. So all we're really doing is taking this, moving it right forward, which means it becomes x equals 4. So let's draw on that asymptote. Vertical line at 4. And then just plot these 2 points. The point 50 is here, 6.7. Negative 1 is here, and we know that's going to get closer and closer to this. We can see that it's moving away this way, so that's what our graph is going to look like. And if we take a look, we can see that it got moved to the right and it got flipped upside down, which is what our reflection was doing. There's our graph. The next thing we're going to take a look at is being able to identify the transformations, which we've actually done this through these last couple problems. It's really just identifying your A, B, H, and K and naming, are they stretches, are they compressions, reflections, translations. So if we take a look at this first one, H of X, we want to really say, it may help to say, what is that parent function? What is all that, we cut out all that extra information, which our parent function, if we just want to call it, we can call it f of x, we can call it y equals, is just this basic thing right here. It's 2 to the x power. So this negative is extra, this 1/4 is extra. That means those things are the transformations that we have. This 2 is not one of our transformations. So we go through and say, all right, A is going to be the numbers being multiplied out in front, which would just be negative 1/4. We don't have any extra stuff in there, so we don't have any other variables. So we just describe what that A represents, which the negative is going to be a reflection over our x-axis. The 1/4 is going to be a vertical change, but since it's a 1/4, it's going to be a compression by 1/4. We take a look at P of x, we want to say the exact same thing. Is what's that extra stuff that we have in there? We see that we have a plus 5, and then we have this 3 out in front. That 3 being multiplied with the log of x, that's going to be the A value. This 5 is being added to it. Now the key thing here is that it's being added to the log of x. It is not being added to the x itself. If it were being added to the x, we would see it inside the parentheses there. But since we don't see it inside there, that means it is actually outside, not affecting the x, so it's going to be our K value. Well, when A is 3, that is a vertical stretch by 3, and our K is 5, that means that we are going to be taking this graph and moving this graph up 5. All right, these last two, I would like you guys to attempt. So I would recommend pausing this real quick and going through answering these couple questions, and then we can go through what the answers are. So the answers. We take a look, we see 3 things going on here added to that log of x. This is the A. This is going to be inside with the X, so that's H, that's K. And so the three things that we should get here is a vertical, it's smaller than 1, so compression by 4/5. This H value, since it's positive, there it's going to be a left 3 because remember that's opposite, so H is actually going to be a -3. That's our left 3, and K is -2, so it's going to be down 2. This one, we have a bunch of things going on here. We have the negative and the 4 out there. Those are both going to be the A. We have this +2 inside with the X, which is going to be our H. And then we have this -3 also with the X, which is going to be our B. So 5 things going on. The negative, reflection over the X. The 4 is going to be a vertical stretch by 4. The H here, again, +2, so H is actually going to be a -2. Is going to be left 2. And then our -3 for our B is going to be a horizontal stretch by 3, because again, we're talking about inside is going to show the opposite, so dividing actually means that we're multiplying the x's by 3, what we would actually be doing to the points. And then the negative there is going to be a reflection over the y. All right, the last thing we're going to take a look at is going through and actually writing out the transform function. Well, it's just about being able to name the a, the h, and the a, b, h, and k, and throwing those into our actual function. So our parent function is 0.2 to the x power. It says translated 2 to the right. Well, going to the right, that means it's going to be the h. Vertically compressed by a factor of 1/3. Vertical stretch compression, that's a, reflected across the x-axis, that is also the a. So we start off with our 0.2 raised to the x power, and let's see what we need to throw in there. Well, we have two values for a. We have the reflection across the x-axis. We have the vertical compression by 1/3. So that means that we're going to take this thing and we are going to multiply it by 1/3 for the vertical compression, and we have a -a for the reflection across the x. This is being our h, and remember, inside with the x is going to show the opposite, so we have x, 2 to the right is going to be -2, so it's x minus 2. There's our new function. B, again, I would like you guys to attempt the natural log of x, 1 to the left, 3 to the right, horizontally stretched by 5. Pause it, take a second, attempt this. What we should get is our answer. This is our h, this is our k, and horizontally stretched by a factor of 5 is going to be D. So we just fill that information in. We don't have an a value. Our h is going to be 1 left. Remember, it's opposite inside. Horizontal stretch by 5, opposite inside. So we're dividing that entire thing by 5. And up 3 would be +3 at the end. That ends our notes for 7-7.